Hello, everyone. Thanks for joining us today. I am Mohamad Hnayno. I am a doctor of engineering working with the research and development department from Ovhcloud. I will present to you today alongside Lionel Faure from Valeo, a presentation about the integration of aluminum heat exchanger in data center. One important thing about Ovhcloud, we have deployed our water cooling system since day one. So since 2003, we have our liquid cooling solution, our own cooling solution within our data center. And we have a combination of two types of technology. The first one is the direct-to-chip liquid cooling in order to cool the processor, the CPUs and GPUs, and air cooling solution to cool the other equipment like the motherboard, hard disk, and RAMs. When we have started with the water cooling solution, we start with 70% of heat load is concentrated to the processor, and 30% of the heat load for the other equipment, for the RAMs, disk, and so on. Today, with the new profile of servers, with the orientation to the cloud computing, we have 50-50 load between the processors and the air-cooled components. So we need today to optimize our air cooling solution. In order to do that, we have in our technology a rear door heat exchanger installed in our rack. Today, this rear door heat exchanger is based on the copper heat exchanger, and we need to optimize this door heat exchanger. So to do that, we have several options. The first one is to use the aluminum microchannel heat exchanger. With this type of heat exchanger, we can benefit from a compact version of heat exchanger. That means we have a smaller heat exchanger with a parallel flow channel inside. That means we have a maximum surface area of heat transfer. That means we have an efficient heat exchanger with a smaller size. But when we will use an aluminum heat exchanger, we have in front of us many challenges. The first one is the corrosion of aluminum inside the data center. The second one is the using of a high water quality inside our data center. That means we need a new material to add it, an inhibitor package inside our water circuit. And we have another challenge, which is a big challenge, the pressure drop inside this microchannel heat exchanger. Now I want to do a small comparison between a finned tube heat exchanger, which is what we have today in the market, and the aluminum microchannel heat exchanger. When we take the same capacity of cooling of 30 kilowatt of two versions of heat exchanger, and when we take the same required airflow for this two heat exchanger, we see that the water side pressure drop, we have an increase of the water side pressure drop of 59%. But we can gain in the air side pressure drop 59%. So the increase of power consumption of pumps, it's equal to the decrease of this power consumption on the fans. So it's a positive point. With the aluminum microchannel heat exchanger, we talk with a lighter version of heat exchanger, about 78%, and 73% when it is filled by water, because we have a much less volume of water inside this heat exchanger. So now, with the challenges that we have with this aluminum microchannel heat exchanger, is the corrosion. Is the main challenge today. The corrosion is increased and developed with an environment with a fluctuation in the temperature. That means we have a relative, not stable relative humidity. In order to control the humidity and the temperature inside the data center, it's a big problem because we don't have the data about the load on each server, on each rack, and on each IT room. So today with Valeo, with the expertise of Valeo in the radiator and the heat exchanger, they developed a technology to galvanize this heat exchanger and have more robust material of aluminum, and controlling the IT room environment by take a safety coefficient for the temperature and the relative humidity, and also by testing this heat exchanger in the cold aisle inside our data center. Now I give the mic to Lionel to explain to us the brazed copper heat exchanger.
Thank you, Mohamad. So thanks for joining. It's a pleasure to be here today with you. So let me introduce myself. I am Lionel Faure, front cooling module manager at Valeo. So you know probably the Valeo company. So it's a major supplier for the automotive industry, more and more focused on other activities beyond automotive, like cooling for data center, but not only. So as mentioned by Mohamad, so brazed radiator is key to decrease the carbon footprint for the rear door especially. So through different factors, so the weight reduction, so the electrical consumption reduction, and also the internal volume reduction of the heat exchanger. So thanks to the brazed technology, so you see here some picture about the differences between mechanical assembly and brazed assembly. So through the brazed assembly, so you have a perfect contact between the fins and the tubes, which is absolutely not the case today on the mechanical assembly. So this is a radiator mainly used today on the data center application. So it's really important to have that in mind, that the earth of the heat exchange based on brazed radiator, this is linked to this technology factor. Other things important also, this is a corrugation on tubes that we are able to create through the process. So you see some example here on the picture, a tube without dimples. So this is what we call corrugation at Valeo, and tube with dimples. So based on these dimples, we are able to increase locally the Reynolds numbers in order to increase the heat exchange. And at the end, to not have the drawback of the microchannel tubes, so concerning the internal pressure drop. So you see on the previous table presented by Mohamad that on internal pressure drop, we have some issues with microchannel tubes, which is not the case with folded tubes. So it's really important to have that in mind, that we are able to manage also these issues. And you know better than me that sometimes for internal pressure drop, we can have at the extreme level some clogging issues. So that means to have completely a circulation block into the tubes. So you have a picture to illustrate what is the bomb content of a typical radiator. So here we are referring to gasket and water tank. It could be in plastic, it could be in aluminum for sure. For reliability topics for data center, we switch to aluminum one and we remove the gasket. It's obvious, it's already done today. So again, the main factor here that you have to keep in mind, this is the brazed technology that allowed a better surface contact between the fins and the tubes. So concerning the solution, concerning the corrosion, because as already mentioned, the drawback of the brazed radiator, this is the corrosion topics. So we have developed with our supplier multi-layer material for tubes. So here you have a cross-section of the tube material. So the first layer is dedicated to the brazing. So this is the clad amount, so 40-45 for tubes, 43-43 for header and things like that. You have the core material itself, so 3003 type material alloy. And the most important one, so the sacrificial layer, to avoid the pitting corrosion and to transfer this phenomenon into a lateral corrosion. So this is really the heart of the baseline solution to manage the corrosion topics. Okay, so this is with this kind of tubes that we will be able to manage the corrosion internal topics, and of course to keep the advantages of what I was presenting on the previous slide about the internal pressure drop level and of course the heat rejection. So it's really important to have that in mind, that this combination of technology is able to fulfill all the requirements and to have at the end advantages on all the topics, not only for corrosion one. So here the illustration is for a tube 230 microns. So of course we have several tubes, 270, 350 and so and so. So it depends of application, but and of course also for sacrificial layer there is different definition. More or less you have to keep in mind that sacrificial layer, the composition, the chemical composition is based on zinc content, again to avoid the pitting corrosion and to transfer the phenomenon into a lateral corrosion. Okay. Here you have an example of a rear door configuration with two different configurations. So on the left side you have the cross-flow configuration. On the right side you have the downflow one. So cross-flow configuration is when the heat exchanger is on the horizontal position and on vertical position for the downflow. So that means that based on this configuration, we are able to replace 120 millimeter core mechanical radiator based on copper technology by a 27 millimeter braze radiator, of course in aluminum. So the gap is huge. That means that we are able, as shown by Mohamad through the table, to divide by 2 the internal volume used for the coolant. We are able to divide by 2 the weight of the exchanger, and at the end through the air pressure drop reduction to have some electrical consumption saving also. So concerning the CO2 footprint is very interesting. And of course, in terms of performance, so we are able for the cross-flow configuration to reduce the surface of the heat exchanger by 26%, so which also of course interesting in terms of cost and CO2 footprint. And even by reducing this surface by 26%, we are above in terms of performance compared to the mechanical radiator used as a reference. So concerning the downflow configuration, it's more cost-oriented, so you have less gap versus the power. So instead of 26% surface reduction, you have only 19% surface reduction, but you are still above the target of the mechanical one. So it's more interesting in terms of cost, less in terms of performance. So after it's a balance, of course, that you have to choose between the different configuration. And as you know, each data center configuration is different, so we can adapt for sure for each configuration. You have to keep in mind also that there is potential gain on the fan system. So this is not the purpose of this conference, but potentially we have things to investigate together on another step concerning the fan system, especially in terms of air recirculation. Mainly what I saw during this event is that there is no shroud on the fan system often, so this is things that you have to think about. So to summarize, braze radiator technology associated with folded tube technology are a good candidate to increase the heat transfer for rear door, and at the end to achieve a target for CO2 footprint reduction for the data center. In terms of performance, there is a huge gap versus the mechanical radiator, so we are speaking of 50% performance increase. Volume, internal volume and weight reduction, the same percentage. So there is really things to do. We have to demonstrate through trials that what I am presenting to you today is working. So this is what we plan in the next months, to put in real condition some braze radiator into a data center to demonstrate that we are at the right level in terms of internal corrosion resistance. As already mentioned, this is the main drawback of this technology versus the existing one. But this is the only drawback. You have only advantages except this one. So if we succeed on internal corrosion resistance, there is a big potential at the end for data center CO2 reduction. Of course, again, as already mentioned, things to do also from fan system side, but it's another story. To conclude, if definitively we are facing to some problem with the internal corrosion test and internal corrosion reliability, we can think about the coolant that we are using. It's not the purpose, again, of this conference, but this is things that we can imagine to use what is used, for example, into the automotive industry. So glycol, what we call glycol, in fact, it's propylene glycol with corrosion inhibitor or things like that to help at the end the system to introduce heat exchanger with aluminum material. So, of course, it's a teamwork, so you are welcome. Every Tuesday we have meeting at 8 a.m. Pacific time, 5 p.m. European time, so you are welcome to participate if you are interested. It's completely open, and it will be a pleasure to have you on board. Thank you. If you have questions, don't hesitate.
As always, please walk up to the microphone.
So the paper will come, it has been mentioned on the previous slide, and will come for end of the year, beginning of next year. So we'll have, of course, more precision about these topics. So if you have a question.
Yes, thank you. So with regard to the corrosion protection, I think you mentioned you're beginning a test soon. I was wondering what testing you have done so far with existing PG25 fluids and what you have seen.
Yeah, so we have experience based on our automotive experience for sure. So we succeed with a Japanese car maker on different requirements. So today we have to extend this experience to data center condition. And as it is completely new for Valeo, we decide to go through a real test on real data center and not to try to perform correlation or to adapt some test to data center potential configuration. So definitively, we have to go through what I can call a real life in order to be sure that our definition withstands the condition of a real data center. So it's impossible to perform correlation based on experience, even from automotive industry. I know very well the subject. We perform some correlation, but it's really, really difficult to extend after this correlation to other configurations. So it's the reason why we decide to go directly to real life, if I can say.
Okay, thank you.
You're welcome. We are done. Thank you.
Thank you.
Thank you very much.